A very good morning to everyone, and welcome to this session on space careers. As I was introduced, I am Kiran, and I work as a propulsion design engineer with Team Indus, which is a lunar lander development company. Before going ahead, if you look at that picture right on your screen, what does it look like? It is a rocket launch, right? So this is one of the most famous rockets in the world, the SpaceX Falcon 9. So as you can see the rocket bellow down, a huge fireball coming out of the rocket as it breaks the chain of gravity and just soars away into the sky, right? So just breaking down what the technical terms are. Normally you call this a rocket, right? So the technical term for it is a launch vehicle because it launches a payload into orbit or into space. So what is a payload? A payload can be a satellite, a spacecraft, or something that can be an asset in space that can go to different worlds, say to the moon or Mars or beyond your solar system. It can be a telescope, it can be cameras and everything. So this is the basic nomenclature. You have a launch vehicle that launches payloads, and payload is something that is a satellite or a spacecraft or something like that. So now that we are clear, and this picture, it's quite magnificent to look at it, right? So whenever you get a chance, when ISRO launches something, you can actually go to Sriharikota and witness a launch. So that is something you should never miss out on. And normally these are huge spectacles. This whole rocket you see right on your screen is about 80 meters tall. So you can imagine how huge it is, what a spectacle it would be, and the sound it would produce and everything. You can see it on YouTube, fine, but going out there and watching it is a different experience altogether. So now we'll just go through an overview about what I'm going to talk about. I'm just going to give you a brief introduction about what rocket science is, and then we'll go into the working principles of the rocket and the main challenges you'd find if you're working on something like this. And then we'll go ahead and talk about space careers and what the future opportunities in this sector are. So humans have always been fascinated about flying, right? Even I'm pretty sure you guys might also have imagined yourself flying out, say like Superman or Shaktiman or even Hanuman. But flying has always been an inspiration. From time immemorial, even in our legends, even in our mythology, there has always been people flying, soaring out into the sky or even into space. You've had legends and mythological creatures who have gone to the moon or tried to catch the sun and stuff like that. So these were always something that you yearned to. That's something you could. You're looking at birds, you wanted to fly, but thousands of years you never could, because it is a difficult thing to do, right? You are not designed to do it, so you have to design some your human body is not designed to be to fly, so you have to design a contraption that can help you fly. So it's very interesting to note that there have been stories, there have been movies about flying. Even in the early 20th century, as in the 1900s, there were stories by Jules Verne, which there was a book called From the Earth to the Moon, which talked about an individual going to the moon. And then we had H.G. Wells' War of the Worlds, which were all very famous books, which had space travel as its main component. And at that time, even movies were coming up, and then you'd know about Georges Méliès' A Voyage to the Moon, which was in itself a miracle, as in it had a lot of new technologies coming in terms of film. But again, it also talked about rocket science and going to the moon and stuff like that. So around that time, you have but none of these people were inventors. In terms of space science, they were all writing stories to inspire people. And it did inspire people. It inspired a lot of scientists who are working in this field, and their whole, the whole imagination was kind of, they were struck by this. These stories helped them and motivated them into going forward and doing stuff that seemed impossible. So it's very important to note that sometimes stories of impossible things can inspire you to do something that seemed totally impossible and make it possible. So these are some pictures you can see on your screen, very famous pictures from the past 5 to 10 years. On your left-hand upper corner, you have an astronaut flying to the International Space Station on a SpaceX rocket. This happened like this year, and this was for the first time an astronaut was flying to the International Space Station in a private rocket. Normally, these rockets are made by government agencies, but here we have a private company taking humans to the International Space Station. And in the middle of your screen, you can see the International Space Station, which is a laboratory which is dedicated to physics, biology, chemistry, material science, and everything. But it exists in space. It exists like 400 kilometers above the surface of the Earth, and it rotates, or rather goes around the Earth. And if you look at this picture, it's very difficult to find, understand the scale of it, but it is huge. It is around 100 meters long and about 75 meters wide. If you've gone to a cricket field or a football field or a 100-meter dash where you run, or a field where you can find that sense, right? 100 meters is a huge distance. And this was assembled piece by piece over the past 21 years. This has been existing for the past 21 years. It is an amazing feat altogether, right? You have humans up to 11, 12 people, hanging out in space, doing experiments, and existing outside the Earth, which is quite unprecedented, say 50 years back. So then on the right-hand corner, you have GSLV blasting off into space, carrying the Chandrayaan mission. And then in the bottom center, you have the SpaceX heavy Falcon heavy boosters landing back, which was again a very a pivotal moment in space, as in normally these rockets are expendable, as in once you fire them, they burn up, they fall down to Earth, you can never reuse them. But here you have rockets that come back and can be reused. And it was a huge pivotal moment in terms of space. And on the bottom left, you can't, this is the Soyuz rocket made by the Russians, which is called as a workhorse because it has existed for the past 50 years and it has been going on and delivering people and cargo to the International Space Station. So these are all amazing things, right? So how do they exist? What is the science behind it? And when you look at all these things, it's so interesting. It's so interesting to be associated with things like this, to work under things like this. So let's get in and see how all these things are done and what can we do to pursue a career which orients towards this. So before we start, we'll have to talk about the founding fathers of rocket science. So back in 1903, there was this guy called Konstantin Tsiolkovsky who published a very pivotal paper called The Exploration of Space and Reactive Devices. This is the beginning of rocket science. It is important to note that this is in 1903. The Wright brothers flew in 1905. So there was this guy talking about going to space at a point where we haven't even flown an airplane. So this guy was a revolutionary guy in terms of science. But another exciting thing is that he was not a scientist. He was a teacher. His parents wanted him to be a teacher, but he was so passionate about science that he did his teaching, but he came back home and he worked on stuff like space and research on space. So he proved that space travel was possible through his theories, and he never saw a rocket fly. But everything was theoretical for him. But through his equations, he proved that space travel was possible, and it was only possible through rocket propulsion, which we'll talk about. And there were some suggestions that what if we keep some, gunpowder or some your Diwali rocket kind of stuff on a chair, and what if I blast off? You might remember that scene from the Kung Fu Panda, right, wherein the panda blasts off into space or into air with a chair that is equipped with all these rockets, right? Crackers, rather. So he proposed that, or he proved that it was not possible. And then he derived the most important equation in rocket science. And again, it's quite enthralling that this was derived at a point where none of these things were tested out, and not even when your aircraft was invented. So he proved that mass ratio is exponentially proportional to delta V by VE. It seems a bit confusing, right? But you all know about exponential curves given the pandemic, I'm pretty sure. So here, what we have here is mass ratio is basically the mass, the total mass of the rocket or the launch vehicle divided by the mass of the payload. So you want your mass ratio to be as low as possible so that your payload is huge. So you don't want to burn the whole rocket and deliver a teeny tiny payload, right? You want your payload to be big also. So he proved that it is exponentially, it varies with delta V by VE. What is delta V? So delta V is basically the amount of energy required to put you in orbit. So if you want to go higher in orbit, you need higher delta V. It's just a direct relationship. If you want to go to, say, Mars, your delta V would be higher. If you want to go to a low Earth orbit or say to the ISS, it will be lower. So VE is basically the velocity at which the gas exits the rocket. You see that fire coming out, right? That is out of the rocket. So that is basically gas expanding out, burning and expanding out. So according to him, or rather exactly, VE is something, the exit velocity is something that cannot be controlled beyond a point. So we can assume that VE is kind of constant. Delta V is again, so wherever you want to go, it is defined. Your delta V is something that you can't change. So he just proved that based on where you want to go, the amount of payload you can carry is just defined right there. And so that is also a very, very interesting result, right? As in, if you want to go to Mars, the ratio of your payload to your whole launch vehicle is this much, say 90%. So that means that only 10% of the total weight of the rocket is the payload. Normally, even in rockets right now, the payload fraction, or the payload, the fraction of the payload divided by the total mass of the whole vehicle is about 95%. As in, only the 5% is the payload. The rest is the fuel, the propellant, the structure of the engine of the launch vehicle, the engines, and all the other paraphernalia. So you're spending all these energy, you're spending all these stuff to put just 5% of the total weight into orbit. And this was defined back in 1905. And this cannot be violated. So this was again a tricky situation. You're at a place where you want to launch heavy loads into space, but that would mean that your rocket itself becomes like predominantly big. So that Tsiolkovsky worked on the theoretical part, and then we had two gentlemen called Hermann Oberth and Robert Goddard. Oberth worked in Europe. He was from Austria, and Goddard was working in the US, and they were working around 1920s and 1930s, and they put the theories of Tsiolkovsky into practice, and they ended up designing rockets that actually worked. So in the picture in the middle, you can find Goddard with a model rocket he made and flew successfully, and you can see the size also, right? It's almost twice the size of Godard himself. And yeah, he was a fully grown man. It's not that he's small, but it was almost that size. But if you look at rockets right now, they are huge. So in the past 100 years, rocket science have started from this very picture right in your front, on your screen. From there to what you saw earlier, huge rockets. So that also kind of proves that technology grows slowly. It takes baby steps. It takes one innovation and then the other, and slowly it grows. So these were the founding fathers, and then we had sudden growth in technology because the World War was happening, and you wanted to build, all these countries wanted to build missiles. Missiles are basically rockets. Only difference is that rockets go up to space. Missiles just try going up to space, and then suddenly they take a U-turn and go and hit a country, right? And the payloads are normally warheads. So there was a sudden growth in technology around the world wars. Then you had the cold space race between US and USSR, the Russians, and slowly all these things grew. We landed on the moon. We went to far, to different worlds. We sent probes everywhere across the solar system. We sent probes that even cross the solar system. We have a Voyager missions that cross the solar systems and is still going on. And so this is how rocket science started out. So how do rockets work? So basic principle of rockets is Newton's third law. You guys might be knowing it, right? It's like the simplest law. Every action has an equal and opposite reaction. So whatever force at which the exhaust is going out of the engines, the same force is exerted on the engines, right? The exhaust gas pushes the rocket up while it's going out. So another important thing to note, so this is a rocket engine, a modern rocket engine. You know how complex it looks, right? So much tubes and stuff was so busy out here, a lot of things running around. And this is a human being for scale. Earlier you saw Goddard with him. The whole rocket was twice his size. Now we can see this is a human being, and this is again a normal sized lady, and the engine might be this small apart. It is almost 4 times her size. So this is where we have come to. So here again we have a cut section view of what you see here, this engine. So engine is the driver, just like you have your engines driving your car. This is something that propels you, that moves you, right? So again, according to Tsiolkovsky, the exit velocity is again, that is also a driving feature in terms of Tsiolkovsky's rocket equation. So you wanted to increase exit velocity to the max as possible. So how do you do that? You all know about thermodynamics. The laws of thermodynamics states that energy cannot be created nor destroyed, but it can be manipulated. It can be converted from, say, pressure energy to kinetic energy, potential energy to kinetic energy. It can be shifted. So then these interesting people, they decided to cheat. So what you do is you cheat nature, or rather physics. All these equations are defined in physics. So you slightly decide to cheat physics, and what they did was, they had this fuel and oxidizer. Rockets carry fuel as well as oxidizer. That is also a very very weird thing to do, because in space you don't have air, you have to carry your own oxygen or oxidizer. Because say if you have a car running on Earth, in the engine, for anything to burn you need oxygen, right? So if a car is running on the road, you have oxygen coming in. It's everywhere, air is everywhere, right? So you have something that will push the oxygen inside the engine, and then it burns. Without oxygen they can never be burning. So because rockets are going into space, you don't have air. That would mean that you have to carry your own oxygen as well as your fuel. Fuel can be equated to petrol, and oxygen can be equated to air. So you have to carry your petrol as well as your own air. So that's why again mass keeps increasing, and Tsiolkovsky tells that if your mass of your whole launch vehicle is increasing, your payload becomes even tinier. So by cheating physics, what these guys did was they decided to pressurize the fuel and pressurize the oxidizer, so that now we can convert that pressure energy into kinetic energy. So this fuel and oxidizer are stored at high pressure, and they are even more pressurized with pumps, and then they are injected into something called as a combustion chamber that you can find around here. These two pictures are equivalent, and then they're burned, and the bonds of the fuel and the oxidizer are released. This fuel breaks up into other chemical components, and that chemical energy is converted into pressure energy. So here in this combustion chamber where the burning happens, it is under high pressure. All this pressure energy is converted, and then you have something called a nozzle, which converts this pressure energy into kinetic energy, as in velocity. And so it comes out, the whole of the gas comes out burning, hot and burning, comes out of the nozzle. So this part is called the nozzle, and comes out of the nozzle at very high velocity, even supersonic. It's always supersonic actually. So it goes out at a supersonic velocity. And Newton tells you that the same force is exerted on the engine itself or on the whole of the launch vehicle. So this is how a rocket engine works. So you can see here, this is an actual representation of a spacecraft, of a launch vehicle called the Vulcan Centaur. And you can see the size difference, right? So this is a huge launch vehicle, and you have a small, teeny tiny spacecraft. So now that was another challenge to be addressed. You wanted to again cheat Tsiolkovsky's rocket equation. So again, what do? Then something else was invented or discovered. You could do something called staging. Staging was, so earlier all the rockets were like, launch vehicles were like, you have a huge fuel tank and an oxidizer tank and a payload that sits on top of it. So then your mass fraction is your mass ratio is already bad, right? Because even when you're going to the topmost side, you're carrying, even when your fuel and oxidizer is expended, you're carrying this whole structure, this whole tanks, which adds a lot of mass that is still being transported. So we decided to cheat physics and divided these tanks. So you have a small tank up here and a smaller tank up here. And when the rocket reaches a point, this portion detaches and the other engine takes over. So suddenly you have a drop in mass ratio. So these are the ways in which we slowly start doing the impossible. We start cheating science, cheating physics to do something that we intend to do. And so we slowly make our payloads bigger and bigger. So that's where we are. That's how you're using these small, tiny tweaks so that you can cheat physics. That is mostly what rocket science is. We are cheating physics to launch higher and bigger payloads by slightly adjusting your inputs and outputs. So earlier in your Tsiolkovsky's rocket equation, your delta V and VE was fixed. They were the inputs and mass ratio was the output. So here what we do is we take it in the other direction. We change the output right away. You change the mass ratio itself. That is again a very intelligent feat you can do. So now we'll talk about how do we launch a payload or a satellite into orbit. So here we have a GSLV with its 3 stages. So that means that the mass ratio improves every time you expand a stage. That and in that way you can take bigger and higher payloads to different orbits. So on your right, you can see a trajectory diagram of a launch trajectory of inserting a satellite into orbit. So here you have a launch vehicle launch itself. So when you see it on YouTube on screens, you'll see this rocket going right vertically, right? But actually it goes vertically till a point and then it takes a turn, because these orbits are elliptical orbits. So if you just go straight up, it doesn't do anything. You have to slowly nudge yourself into the trajectory of that orbit. So most of the rockets are launched, almost all of the rockets are launched in the same direction of the spin of the Earth, so that you can use that small angular momentum of the spin of the Earth. It will be in your favor, and so you can expect less power or less fuel and oxidizer, less propellant, and you can reach greater or higher orbits. Now, that is also kind of a cheating science to an extent. And so the launch vehicle stages, it drops some of its stages down, and the launch trajectory is designed in such a way that all these stages, when they separate, they just drop down to Earth. So the launch trajectory is designed in such a way that this drops down into sea and does not cause any problems. So we go up like that, and then the satellite is injected into a lower orbit or a geostationary transfer orbit, which is used to transfer from one orbit to another. So you want the satellite to be in a geostationary orbit. So you insert it into a transfer orbit, and now the work of the launch vehicle is done. So all these satellites have their own propulsion, they have their own engines, and those engines take over at this transfer orbit point, and they burn and propel the satellite to a higher orbit. So this is how it is inserted in orbit. Now that is like half of the work, right? You're inserting it, but the main work is how does the satellite perform? The satellite has to give some useful information or useful data. Otherwise, what is the point? So these satellites might have payloads on them, say cameras, say infrared cameras. They might be providing internet to people, or they might have other sensors that can predict change in weather patterns. They can predict cyclones and stuff like that. So, and another important thing is you have to keep communicating with the satellite, right? So you can't just leave a satellite up in space and just sit back there. So for that, we have ground stations for communication. So these ground stations are spread out across the world. There is a network called Deep Space Network of huge antennas. So if you go to a television station or something, or say a radio station like the All India Radio, you'll find these huge antennas, right? Of these whole conical antennas. Like those, there are huge antennas across the world that is spread out, so that at all points the satellite should be visible to us. So imagine the satellite is on the other end of the other side of the Earth, it won't be visible, right? So you have a network of that, so that wherever in the orbit the satellite is, we are able to communicate with them. And then you have solar panels to generate power. So that is one very good thing, that you have sun that is just giving out power everywhere. You can just have solar panels that can power the systems, the computers and different sensors and cameras and whatnot on the satellite. And so that is also a very important section. And you have batteries for backup. So at points when the satellite is again, the earth is eclipsing the sun, you can have batteries that can power the satellite or give auxiliary power to the satellite. And then you have attitude control. Attitude control is basically, so if you have a camera mounted on a satellite, you want the camera to always look at the earth, right? You can't have the camera looking at in space. So you have smaller thrusters mounted, strategically across the satellite, which slightly nudges the whole satellite to point in the exact direction that you want it to. So these are again three important facets of a spacecraft that needs to be taken in kept in mind. So now, what are all these different sections are called subsystems. So the important subsystems on a spacecraft are propulsion, which is the engines, and which provides energy to the spacecraft to move about. Structure, which is when you're a spacecraft, you're moving at high speeds, right? You're going faster than the speed of sound, so you have a lot of compressive loads on you, and this whole structure itself should be designed in such a way that it can handle all of those things. We talked about attitude control. Then you have telemetry and tracking, wherein you try to discern where exactly in the orbit the spacecraft is. Then you have communication, power, and thermal. So thermal is also an interesting subsystem, because space is actually very cold. You would expect space to be hot, but no, space is really, really cold. Even though you have the sun, but because it's a vacuum, the only means of heat transfer is radiation. You don't have conduction, you don't have convection. All you have is radiation. So that means that it's really, really cold. So, and the electronics we design on Earth can survive certain temperatures. It can't go beyond, it can't handle very low temperatures. So this, you might have seen pictures like this, wherein all the satellites are wrapped in this gold color, sheet. So this is called MLI, or multi-layer insulation, wherein all these components are wrapped up so that the heat is not escaping. Here again, we are doing a small cheating, that when electronics function, it generates heat, right? So this MLI keeps that heat trapped inside and helps the electronics to again function in the temperature ranges which they are comfortable in. So you're using their own heat to keep them, hot. So these are basic spacecraft subsystems. And now let's talk about space careers. So space careers, you have a lot of options. Either you can do engineering, which I dealt about. I talked about all the subsystems and stuff you can work on. Then you have science. Science would mean astrophysics, finding out where, how stars originate, finding planets and stuff like that. Then you can have law and management. Space law is something that's coming up, as in, so what happens if two different countries land on the moon and lay claim to some patch of land? What rules do they follow? Do they follow rules on Earth, or do you have to have separate laws for that? And that is also a very interesting perspective. So also in terms of science, you have space medicine, you have a lot of stuff like that. And then if you can find something where all the companies right now are lacking, you could actually start a company and you could do something like that also. So I think there was a quiz about what are your interests. Yes, so I'd like to hear which lead character from these following films, space-themed films, would you like to emulate? I'll just wait for you guys to fill up the answers. So I'll just talk about these pictures. So this is a rocket engine being tested. So before you send out all these things, you have to test them out. So you keep it on the ground and test them. So this is a space telescope, which is in Hawaii actually. And it's one of the most beautiful places to be. This is the James Webb Space Telescope, which is again going to be launched this year, and is one of the most. It is intended to be the best space telescope out there. It's a radio telescope, and this is the Mission Control Center in NASA, wherein they keep track of the ISS and the workings of it, and stuff like that. So one more thing about how space is hard. So in terms of space, you have one shot to do everything, right? Imagine you're making a car and your battery doesn't work. So you sell 100 cars and none of the batteries work. You can always tell your customers, okay, you can come back, get your battery fixed. But what happens if you make a satellite and its battery doesn't work? You can do nothing, right? You have already launched it. It'll just lay there, no power, and everything, slowly everything will die, and there's nothing you can do about it. So space is a one shot. You have one shot to get everything correct. So that is the most difficult part of science, of space, that you have to get everything right in one shot.
My apologies. Should I close the survey and share the results, or?
Yeah, please do.
Yeah. So I think gravity is 33% of the respondents.
Oh, cool.
So is Interstellar.
Okay.
And then Apollo 13 is 18. Martin is 10. First Man is 5. Arrival is 1%. That's it.
All right. So most of you guys are interested in being astronauts or doing science in space. That is also very cool. So I haven't mentioned astronaut here because astronaut is something that's totally different. Astronaut takes in all these perspectives, puts together, and then you have an astronaut. There's no criteria for what you require to be an astronaut. You can be from the engineering field, you can be from the science field, you can be a teacher. But you have to be an expert in your field, and you have to know everything about most of the things about all these fields, right? And you have to go through endurance testing and stuff like that. But being an astronaut is one of the most coolest jobs in the world, right? So that is also an interesting part. So best luck for everyone, because India also in the coming years will have an astronaut program. Even right now we are having one. We have already selected some test pilots from the Air Force. That's how normally it happens. These test pilots in the Air Force, they fly jet aircrafts which go at very high speeds, and their endurance is very cool. It's the most stringent requirement to be have that endurance to handle all these huge loads and stuff, huge G forces when you're on a launch vehicle. So that is also a very interesting career path to take up. So now we'll just talk about in general, not even about space. How do you decide a career? It can be applied everywhere, right? So first thing I'd say is find out what your passion is. So some people might be interested in space, some people on something else. So find your passion, and then list down some future opportunities you can have in that career, and then talk to other people who work in that field and try to find out what are the most important characteristics required to be in that field, and then align yourself in that perspective. If it doesn't work out, it doesn't, but you can always find your strengths and redefine your passion as well, right? If you're strong in some perspectives, you will surely have a passion that aligns with that, and then identify your goals and start working on them, and surely you'll achieve a career you would enjoy. So you may have heard people tell that, oh, I don't enjoy my job. That's basically because they chose the wrong career. So if you can spend some time, whatever age you're right now in school, it's fine. So if you can totally make out what you want and what you want to work on, it just changes the way you look at careers, or the way you look at office, right? So you'd be excited to go to office. It might be like going to a playground and playing. You'll be really interested in going to office every single day. So that's why it's very important to choose the right career and to assess yourself, assess your skill set and your passion, and find something that aligns with all these things. So now we'll talk about space careers. So in order to get to all these subsystems I talked about and more, I'm dealing about only engineering. So you can either choose these streams like mechanical, aerospace, electronics, electrical, and computer science. Even computer science is applied extensively in space. So if you do these undergrad courses, you have a overall idea of stuff, how it works. So then you'll have to differentiate yourself from the crowd. For that, you can do a lot of internships, you can do projects while you're doing your undergrad, something that is related to space, and that will give you an edge over other people so that you can pursue what you want. You can choose projects and internships based on your interest and pursue them. Another option would be do a post graduation, which which would align you in a more pointed way. You can say choose avionics or robotics or control systems, which aligns you perfectly for a job in that sector. So this is like a basic outlook on how to go about in terms of careers. So you can start from the undergrad. You should have an idea of what you see yourself in the next 5 to 10 years, which field you want to work on, and it doesn't matter where you are right now. It's about working towards your goal. Maybe it might take some time. It doesn't matter. You can always put in more effort and expedite it and get where you want to go. So now we'll talk about what the future holds in terms of space. The future of space in the coming 10 to 15 years is going to be very exciting. In the future, you can have countries and private space agencies landing on the moon or even the Mars. Then you can expect swarms of satellites that provide internet and security and weather data and lot of things. And these huge data can be crunched and analyzed, and that can also drive the technology forward in terms of say internet of things and lot of applications that come with satellite data. Then you can have driverless cars, although we have some driverless cars, but it can be democratized and can be taken everywhere. If you have the support of satellite data and stuff like that, then you can have probes that go to far-flung planets, say Mars or beyond. And then you can have one of you might design some other reusable rocket that is even better than what you see right now. So all these parts are out there, and the next 5-10 years in space is going to be really interesting. And if you are somebody who enjoys all these challenges, it would be the best place for you to be. So thank you all for sitting through this session. So I'll take questions now. So Jagrat is asking, sir, I want to be an astronaut. How can I be? So I kind of dealt with that question earlier, right? So being an astronaut right now is a bit difficult, but over the past of the next 10 years, it might be more interesting. So astronauts are not space travelers. They are traveling to do some particular science. So that is something people miss out on. So you have to be an expert in a certain discipline, and then you become an astronaut. You don't become an astronaut, then be an expert. You are an expert in something, and then you're an astronaut who goes to space and does the same science in space. So that is that's how it is. And it's like you have to be an expert, you have to take up science or engineering or stuff like that, and then all these countries have astronaut programs. You can apply for those. Some countries have stringent requirements that you should be a air force pilot or things like that, but that is also kind of achievable. So that's how you go about. So Sohan asks, I want to be a quantum physicist, how can I be? So that is more into science and not too much about space. So you can take up physics in your undergrad. You have many great institutes in India like TIFR, the Tata Institute of Fundamental Research. You have ISRO, the Indian Institute of Science, Education and Research. And all these places, you can take up undergrad courses in physics, and then slowly you can graduate into quantum physics, which is again a very advanced topic. So is nanotech actually true? Given in Avengers Infinity War. Okay, that's a bit fantastical. The Avengers Infinity War kind of things are not true, but nanotech is very much true. Nanotech, you can find nanotech everywhere actually. So it is applicable, but not to the scale that you see it in films. Is it true that black hole is the way to another dimension? Nobody is sure. Research on black holes is still going on, and black hole just means that whatever goes into a black hole just vanishes, or just gets compressed into a teeny tiny space, and all the mass is concentrated in that small packet. So we know what happens, but nobody knows what happens behind the black hole. You have theories. Nobody has, we haven't sent a probe that goes near a black hole, takes observations and stuff like that. We have telescopes looking in black holes and modeling them. That's all. How can you join ISRO after completing 12th standard? So you can't join ISRO after completing 12th standard. You have to do your engineering, and then ISRO has many exams. Based on engineering, you have to do your undergrad in engineering, and then they have exams, all India exams, which you can appear for, and through those exams you can get into ISRO. I want to know how rocket produces smoke, but I've read that it produces water in form of vapor. Actually, rockets can use different kind of fuels, right? So if it's the fuel is hydrogen and oxygen, when they combine and combust, it produces water vapor. But if it's a different kind of fuel, say you can have hydrazine, which is very some other kind of fuel, and you have nitrogen tetroxide. When these two combine, you can find a very orange color flame and smoke. So ISRO engines normally use this, and the flame, based on the flame color, you can actually tell what the propellant combination is. So if you look at the SpaceX launches, it is very the flame is not reddish, it's orangish, but it's very opaque, right? So from that you can tell that they use kerosene as their fuel. They use kerosene and oxygen, not the kerosene you can get in your shops. It's a very high grade kerosene. So Priyank asks, what are the different fields in aeronautical engineering for choosing a career? And I've heard that aeronautical engineering itself has many subdivisions of careers. Yeah, of course it has. So aeronautical engineering can have propulsion, you can have structures, you can have thermal, you can have aerodynamics, control systems, and a lot of it. So going there, it's about finding what your specific field is. Of course, you might be interested in aeronautics, but it's about finding a specific interest. that when you know more about it, you'll be able to tell. What are the future projects of ISRO? Future projects of ISRO would be the Chandrayaan 3 mission, wherein we are going again to try to land on the moon. Then you have the Aditya L1 mission, wherein we are going near the sun and try to take observations. We have the Mangalyaan mission, which and many more missions coming up. And then one important mission you guys might be missing out is something called the AstroSat mission, which even till date, it's giving great observations. It does not have that huge fanfare of Chandrayaan, but it's something that is still giving very productive science data to the community. Sir, to go to ISRO, what qualifications are needed? First things first, if you want to join ISRO, you would need to be an engineering graduate if you were talking about this discipline. And then you can have your undergrad in any of these engineering backgrounds. And then you can either have a postgrad, which again, lets you specify where you want to go to. You want to be an exobiologist, how can I be? So space biology also, it's a very interesting perspective. So again, you can do your undergrad in say biology, and which is more oriented towards space. So most of this space stuff happens, the biology and space medicine happens in microgravity. So that another interesting point is that, so scientists were always confused. So what happens if a human being goes to space? What all things change on your body physiologically? So it turns out that nothing changes as much. Your brain functions properly, everything is right. Only problem was that your bones started losing bone density. So when you come down after a huge, long space mission, your bones are a bit as not strong. The way you bend, it might not be as strong as when you come back. So for that, you do a lot of exercise. They eat a very controlled diet, and that is also kind of manageable. So what is a wormhole? Wormhole is a concept wherein if you have a black hole and a white hole, which is the opposite of inverse of a black hole, you can travel from one dimension to the other in the a very small time. But that's also a scientific concept per se. So what does nozzle convert into? All right, so we talked about the nozzle. So the nozzle converts the pressure and chemical energy into kinetic energy to convert to give out huge momentum. So rate of change of momentum is force. So that is what drives the rocket forward. So you're a commerce student. If you're a commerce student, you don't have opportunities in terms of engineering, but of course you can have opportunities in terms of law and management and stuff like that. So coding in space biology. So one thing I'd like to tell is coding is a very valuable resource to have for yourself. Even at any point you are in your school, you can always try to hone your skills in coding, because engineering is mostly about fitting physical things into mathematical equations and predicting what happens in the future. You want to predict, okay, I have this big an engine. How far will the rocket go? That is all equations, right? So, most of these things cannot be worked out on a paper and with a paper and a pen. So, coding is a very, very, very requisite skill set here. And it's not that difficult as well, right? So if you start right now, you can always become better at coding. So another question will be, light cannot escape gravitational pull of black matter. Then how black hole pictures are taken? They are not taken with normal your cameras. They are even the black hole picture that was released a year or two back. It was based on X-ray information that was taken out, and then a huge amount of data was crunched, and then it was manipulated in many ways using their equations, and then you got there. It was not taking a picture as you would imagine. So can you get into ISRO through B.Sc or M.Sc? Of course, ISRO also has many science applications. So if you do an M.Sc or a B.Sc, of course, you'll have opportunities. So another question would be, first aircraft was built by an Indian even before Wright brothers. You are mistaken. That's not true. Wright brothers were the inventors of the aircraft as we see right now. And another question is, how does the satellite enter the orbit around Earth exactly and not move anywhere in space? So that is what engineering is, right? So making the rocket and making all these machines behave exactly the way we want is engineering. So you have these launch vehicles and rockets. They have computers on them. Then you write software onto these computers. There is something called flight software, which is written hard coded into the computer, and the computer makes the rocket behave in the way you want it to behave. So that is why you have all these you have whatever you want to do, the rocket does. So another question is, I want to become an Indian Army fighter pilot. So what should I do? Passing 12th standard. You can take up engineering. So sometime there are applications where you can directly join the army, the Air Force after 12th standard. It's always better to do your engineering and then get into this field. So another question is time travel possible? As far as we know, it might be, but not really. Then, sir, can I go to can a spacecraft like UFO can fly? Yeah, UFOs could exist, could not. We don't have much information about that. There are some people who claim that they've seen those, but you can never be sure. Is it difficult for a quantum physicist? Yeah, is there any? Can I get a job in SpaceX? Of course you can, but because it's rocket science, some areas are controlled by the government, so you cannot get jobs in some sectors. But of course, you can get a job in SpaceX.
Sir, so if I take computer science or any other category in under technology, so can I be an astronaut in NASA?
In NASA, so thing about NASA is that the astronauts should be American citizens. So it doesn't matter which discipline you come from. It depends on what research you're going to do. So it is totally possible, but it would mean that you would have to become an American citizen. That would be the only roadblock.
I don't necessarily mean NASA actually. It can be even ISRO also. So is it possible?
All right. Yeah, it is possible. It is possible. Totally possible.
Okay, sir.
Yeah.
Sir, how can we join IASD?
Okay, so that's a very important question. So IASD, you can join IASD through entrance exams. It happens through the IIT JEE mains exam. So based on your IIT ranks, you can apply to IASD. And IASD has a very targeted program. So you have programs in aerospace, avionics, and physical sciences, which is exactly targeted towards space, and so that they are the kids who complete their courses there can directly join ISRO. So IIT JEE is the selection criteria to join IISD.
So Dyson spheres are real, and can we extract energy from black hole and use it?
Yeah, so Dyson spheres are also conceptual things. For them to exist, humanity will have to wait for another couple of centuries, probably. So it is an interesting perspective to think. So humanity is very low in terms of extracting energy. So human civilization, we get to extract a small percentage of what the sun is giving out, right? So Dyson spheres are possible if we can extract the complete energy of the sun. So it might be possible. An alien civilization sitting somewhere in deep space could be doing it, but theoretically it is possible. But of course, you'll have your technology should be so advanced that it's quite not possible in the immediate future for humanity. And extracting energy from black holes, again, black could be a possibility, but I don't want to comment on it because I'm not an expert on that topic.
Hello, sir.
Yeah, hello.
So, my question is, can we take up this career after completing engineering in private colleges?
Yeah, sure. It doesn't matter
Sir,
where
and
you study.
what is the
Yeah,
criteria and scope of institutions if I want to
yeah.
pursue my career as a quantum physicist?
Yeah, okay. So it doesn't matter which college you come from. It all matters is your skill level and how good you are, right? So if you are good, it doesn't matter where you come from. And taking up quantum physics, again, I was talking about in terms of engineering, you want to take physics as your major. Again, if you're done your engineering, you can do your master's in physics. That is also possible, or you can do your undergrad itself in physics and then move towards quantum physics because it is a very advanced topic, right? So that is how we go about.
Thank you, sir.
Yeah, AI is involved in space. Of course, AI is being integrated into space. Nowadays, you have multiple satellites that communicate with each other and take decisions by themselves. That is a that's an emerging technology that also does exist. And the future scope of AI and technology in rocket science is immense. Thank you. So thank you for being part of this. You have been an amazing audience. The questions were also really amazing. So I'm really grateful.
Look, I told you so.
Yeah. Yeah.
Yes. In fact, that's something that we have been enjoying. Kiran, it was a pleasure having you. Right. Thank you so much for coming over.
Yeah.
I am getting requests from a couple of schools for further sessions. A lot of schools in Middle East were complaining it being a working day today.
Yeah.
Right.
Yeah.
Hoping to have you back again. Right.
Yeah. Sure.
Love to keep bothering you.
Yeah.
Okay, people. That's it for today. I wouldn't say this is the first time, but we do have a constraint of time, and we'll have to call it a day. Thank you so much, everyone, for participating, and a big thank you to Kiran for giving your time. I'm closing this session. Thank you so much, everyone. Bye-bye.
Thank you, everyone, and have a good day.